Good evening, engineers. Today I am going to present a general overview um, on the requirements of ACI 31819 for using high grades reinforcement. When we say high grades reinforcement, in fact, I mean grade 550 megapascal and 690 megapascal. Um, I will discuss this topic from the point of view of ACI 31819 rather than 31825. But I believe if you understand the intent of ACI 31819, you will understand easily the ACI 31825 requirements. I believe no significant changes between both of them. Okay, let's start. I will try to be fast as can as possible. The main objectives. We will discuss the types of non-prestressed steel reinforcing bars, development and supplies requirements. We will discuss the additional requirements in ACI code for using high-grade reinforcement for different structural members, same like beams, columns, twist slabs, and also some special members. Also, we will discuss the limits imposed on concrete compressive strength. Also, we will discuss strength reduction factors and benefits of high strength steel reinforcing bars quickly. What about ACI 35020 for the environmental structure? Does this code permit to use high grade reinforcement or no? And also I will give some notes about ETABS capability about using high grade reinforcement. If you would like to read more about this topic, I strongly recommend those technical notes from CRSI website. And also you can read from the main code ACI 318, 19 or 25. Also David Fanilla, one of the best persons, he I believe he discussed the same topic also with ICC. So let's start. First of all, you have to know that in ACI code there are different types of non-prestress deformed bars. The first type is called A615. This is carbon steel. In fact, this is the most common reinforcement type used in Dubai and in UAE in general. If you see table 22.1.3a, this table presents the minimum requirements for ACI for A615 reinforcement. So for example, if you would like to use grade 420 and the type is A615, as per the code requirement, you have to satisfy minimum tensile strength 550 megapascal for this grade, and you have also a limit on the ratio of actual tensile strength to actual yield strength. These are minimum ratios, so you have to satisfy those requirements, and also these requirements can be found also in ASTM A615. Also, this table is from ASTM A615, the same requirements in ACI code, but with more additional details. Also, we have another type of reinforcement. This type is called A706. A706 mainly is used for special systems. This type of reinforcement is very good type for seismic resistant structures in special or in high seismic regions, or seismic design category and higher, seismic design category D and higher, let's say. If you look if you see table 20.2.1.3b, here it was a table A, here the table is B, you will find that for A706 reinforcement we have additional requirements when compared to A615, because again this type of reinforcement is used for special systems. If you look here we have minimum tensile strength, and also here we have a ratio of actual tensile strength to actual yield strength. These first two requirements are similar to what are required for A615, but here we have additional requirements. Same like here you have a minimum yield strength, maximum yield strength, and also here we have fractal elongation requirement. If you look here the code specifies also a maximum yield strength. If you look for A615 requirement, you will find that there is no upper limit on the yield strength. So this is very important. One of the main reasons for that if you have a special system, you cannot use a reinforcement with actual strength or yield strength higher than the value specified in the design calculations. In special members, we are calculating the shear or induced shear from the probable moment. Probable moment is calculated from the expected strength of the material. So if you increase the strength of the material, you will increase the induced shear on the joints or within the joints. That's why this is very important. If the code need you to use A706, you have to know that we have upper limit on the yield strength. You cannot use any high yield strength than the maximum value. So for example, if you would like to use a grade 690, your actual yield strength shall not exceed 814 megapascal. But this is not required for A615 reinforcement. Here also we have uniform elongation requirements, 9%, 7%, 6%. This is based on the bar diameter, and also for large size bars, here we have 6% as a minimum elongation. Again, these values are minimum. Also, this is this table 2, tensile requirements for A706 from ASTM also. Okay, I believe that ACI 31825 deleted or removed these tables because these tables already are available in ASTM now. So instead of repeating the same tables in ACI, so now ACI refers only to the ASTM number, so you can get the requirements from the ASTM instead of repeating the details in the code. Also, if you if the code requires to use A706, there is also additional requirement for the bars used in earthquake resistant structures. This requirement is related for the radius of deformations for the bars to avoid fatigue or inelastic fatigue cracks. So you have to satisfy also that. Also, we have other types of non-pre-stressed steel bars, same like ASTM A996, ASTM A955. This is stainless steel. Also A1035. This is low carbon reinforcement also. Okay. Also here I would like to highlight that ASTM A615 bar sizes larger than 57 millimeter are not permitted. Also, in ACI code, we have different types for plain bars: A615, A706, A955, A035. Plain bars are permitted only for spiral reinforcement used as a transverse reinforcement for columns, shear and torsion, or confining reinforcement for splices. So you have to know that if you would like to use a plain bars for these purposes, you have to understand that we have a specific types. Also other types seem like welded deformed bars, heated also deformed bars. So if you would like to use heated deformed bars, you have to know that the A970 or ASTM A970 covers the requirements for this type of bars. Okay, here ACI table 20.2.2.4a. This is the most important table in ACI in chapter 20. Here in this chapter, you will find the maximum value of yield strength permitted for design calculations. This is very important. The key word here is the calculations. So we can understand that we can use higher strength, but we cannot assume or we have to, or the code need you to specify upper limit of your assumed strength in the calculations. For example, I will give you one of the common example. Typically in the market, especially in Dubai, we are using a grade 500 megapascal reinforcement. So we are using grade 500 megapascal when we design our structures, but when we design the shear reinforcement, we have to assume 420 megapascal in the calculation. Also, if for example, if you have a raft and inside this raft we have a reinforcement with 500 megapascal grade, and you would like, or due to site constructions, we have to provide a construction joints. Within this construction joints, we have to check the shear friction requirements, assuming a field of 420 megapascal. So there is a difference between specified yield strength in the calculations and the actual yield strength. This is very important. You have to understand that. Okay. If you look here, if you would like to calculate the flexural reinforcement or the reinforcement required for axial strength or the shrinkage and temperature reinforcement, first of all you have to determine your structure. Do you have special system or other systems? For example, special systems seem like special moment resisting frames or special shear walls. Other systems seem like ordinary shear walls. Okay, if you have a special system and you have special moment resisting frame, the code does not permit you to assume in the calculations a value of yield strength higher than 550 megapascal. You have upper limit. Okay, if you would like to use a special shear wall or special structural walls, the code permits you to use 690 megapascal in your calculations. This is very important. Okay, if you have, for example, ordinary structural shear walls, you can use or you can assume a design value of yield strength up to 690 megapascal. This is the first point. Second point, you have to look here. If you remember, just right now we have discussed the type of deformed bars. Why? For this point. If you look here, as per the code, in special seismic systems, we have to use only A706 bars. But for other systems, same like ordinary shear walls, as per the code, it's permitted to use A615, A706, A955, A996, A1035. As you can see here, because here we have ordinary systems. When we say ordinary systems, so we can expect low seismic hazard or mid seismic hazard. So the code permits to use different types of deformed bars. But if you have a special seismic system, so you are in a high seismic region with high seismic design category, as per the code, it's not permitted to use A615. So you have to understand this point. Okay, if you would like to calculate the lateral support bars, also as per the code, you can use 690 megapascal in special systems, but for other systems like ordinary systems, you can assume upper value of 550 megapascal. So here we have upper limits on the calculations. Also, a similar example, I believe that it would be useful for you engineers. For one-way shear strength, as per the code, the maximum FC prime used in the calculations for one-way shear or two-way shear is around 70 megapascal as FC prime or cylinder strength. What does this mean? This means that you can use FC prime with 80 or 90 megapascal, but for calculations of shear strength, you can use only FC prime equal to 70 megapascal as upper limit on the design values in the calculations. Type. Here also, if you look here, this table is from 318.14. This table is from 318.19. In this table, for flexure or axial strength or shrinkage and temperature, the maximum permitted value is 550, while in ACI code we have 600. In ACI 19, I mean, we have 690. This is the first difference. Number two, in the special systems, you can use only 420 megapascal. But in ACI 19, one of the major changes that the code now permits to use high grade reinforcement in special systems. But in 14 version, the maximum value or permitted value for calculations was 420 megapascal only. Also here, for shear calculations, if you have a special systems, the code permits to use 550 megapascal or 690 megapascal. This is based on if your system is special moment frames or special structural walls. But if you would like to calculate stirrups, ties, hoops for other systems, same like ordinary structural shear walls, you have to use a value 420 megapascal. This value we are using frequently in our daily design. But for example, 550 is not permitted. You have here other types of or other type of deformed bars, welded deformed bars. Welded deformed wires. I have not used this type of deformed bars before, in fact. Here also, I need to highlight that you have always to read the footnote. Footnote is very important. So, for example, here in ordinary systems, it's permitted to use a grade reinforcement up to 690 megapascal, but you have to read 3 and 4 footnote. In fact, these footnotes are related to intermediate moment resisting frame. So you have restrictions or additional restrictions on using high grade reinforcement for intermediate moment resisting frames. Okay. For anchor reinforcement, in fact, in special seismic systems, you can use a strength or yield strength up to 550 megapascal, but as I said before, the type of reinforcement shall be A706. Now we can understand again A706 I will say has more restrictions in ASTM specifications, more than A615. The most common type of reinforcement in Dubai is A615. Again, in ACI 318 14, the using of high grades reinforcement were prohibited in many cases, but ACI 318-19 now permits to use the high grade reinforcement in different cases, in fact. Okay, again, for grade 550 megapascal used for anchor reinforcement in seismic design category C must conform to ASTM A706. In fact, rare of engineers aware for this requirement. This is required for seismic design category C, not only D, E, or F. So as you can see here, the type shall be A706. Here also, ACI 20.2.2.5. If you'd like to calculate the required reinforcement for moment action, axial force, or combined effect, for special shear walls or structural walls, I will say structural walls because shear walls or structural walls can be a shear walls or a flexural walls, but for this purpose, you can use or you have to use only A706, and as per ACI code, it's permitted to use a grade 420, 550, or 690 megapascal. For special moment resisting frames, you cannot use 690 megapascal. The maximum value is 550 megapascal. Again, A706, A706 here. In fact, ASTM A615 grade 550 and 690 are not permitted in special seismic systems and anchor reinforcement in seismic design category C, D, E, and F. This is very important note. But the code, in fact, give you an exception if you would like to use A615 grade 420. So in case if you have a special systems and you would like to use a grade 420 megapascal, it's permitted now by the code as an exception to use A615 type of reinforcement in lieu of A706 grade 550 reinforcement. But you have to satisfy additional requirements. You have to look into the code to see what are the additional requirements needed to be satisfied to use A615 grade 420 megapascal for a special systems. Now, in fact, I would like to discuss the development and splice length requirements. In ACI 318-19, there is a new factor added to the development length equations called grade factor. This table 25.4.2.3 presents a simplified equations. These simplified equations will result always in a very conservative values of development length. Anyway, if you look here we have psi sub g. This is a grade factor to take the effect of using high grade reinforcement. But before going into the next step, I would like to add a comment here that I don't recommend to use these simplified equations. I recommend always to use the detailed equation. This is the detailed equation. I will give you an example from James White book. If you go there, when he calculate the required development length from the simplified equation, he got a development length almost double the development length required by the detailed equation. Detailed equation always is recommended to be used. In fact, in my high-rise structures, this made a very big difference. If you would like to use this simplified equation, this will be very fast for calculations, but this will cost a lot later on. That's why I recommend not to use these simplified equations, and I would recommend to use the detailed equation in ACI code. Anyway, if you look here we have reinforcement grade. This is, by the way, this factor is a new factor in ACI 31819. For a grade 420, the value of the factor is 1. For a grade 550, the factor is 1.15, as you can see. Okay, as per the code, you can use high grade reinforcement. So 550, in fact, if we divide the 550 by 420, you have 30% additional yield strength. But again, you have 15% additional requirement for the development length. Okay, if you'd like to use 690, you have to increase the development length by 30%. This is very important. Okay, now some engineers will ask, what if I have 600? Because now in Dubai, I started to see a new type of reinforcement called E600. 600 is something in between the 550 and 690. In fact, the relation here is not proportional. If you look here, for example, 280 and 420 is 1, both of them. So if we need to say that it's proportional, so this should be 1, this should be, for example, 0.6, something same like that. But if my personal opinion, if I need to take a grade in between, this is my personal opinion. In fact, this is not the main interpretation of the code. I can make interpolation. But I sent an inquiry for ACI stuff before, and they said to me that in fact the relation is not proportional, and some engineers will take the upper factor, and some engineers maybe can take the interpolation. Other engineers can take the lower value. So in fact, it's something not proportional. But for me, personal opinion, I prefer to take the interpolation. Okay, so this is the detailed equation of ACI code. Here we have a confinement factor. This will take the effect of additional cover and also additional stirrups or confinement bars or transverse reinforcement. This equation will give you a very perfect values in the vertical members. In fact, in one of my projects, for example, we have T40, sorry, T32, a lot of T32 bars. T32 bars typically require more development length. So when you try to use the detailed equation, you will get a reasonable values. Okay, I need to check if it's recording. Okay. Also, if you look in the or into Provision 25.4.2.2, you will find that the code need you to provide maybe additional transverse reinforcement along the development length if you would like to use a strength or yield strength higher or equal than 550 megapascal. So as per the code, if you would like to use high grade reinforcement, he need also additional confinement. This additional confinement can be calculated simply from this equation. By the way, this is KTR. If you look for this, what the code need you, K sub TR shall not be smaller than 0.5 diameter of the main bar. So this is known. This is equal to the half value of the diameter of the longitudinal bars. 40 is a fixed value. ATR is the number or the area of the number of the area of the transverse reinforcement enclosed the bars being developed. So also the number of legs are known, and the area of these legs also are known. N is the number of legs. Now we can calculate the spacing. In fact, the spacing, we are talking about the spacing along the body of the beam, or along the height of the column, or along the height of the wall. So this is very important. Maximum as of transverse reinforcement shall be satisfied along the LD distance. This requirement is not to be satisfied along the beam length or along the full height of the column. No, only along the development length. So the code, okay, the code says, in fact, yes, you can use high grade reinforcement, and you have to increase the required development length by 15% or 30%, but again, you have to make sure that the transverse reinforcement along the development length is not less than a certain value. Provide sufficient confinement to prevent splitting failure of these bars. Because if you would like to use high grade reinforcement, in fact, the area of the bars, required bars, will be less, the strength is more, the stress is more. So if the bars are subjected to higher stress, so we have a risk of splitting failure. That's why the code need you to provide a transverse reinforcement. By the way, this requirement is mandatory. Also, if you would like to calculate the standard hook development length in tension, by the way, don't use the equation from ACI 19. Now we have a nice equation in ACI 318.25 will give you lesser values significantly than this. This equation, I believe that this equation is not correct, and that's why the ACI 318.25 returned back the same equation of ACI 318 from version 14. So don't use that. But anyway, if you'd like to use high grade reinforcement, here you have to increase the yield strength, and this will increase the LDH. Again, in ACI code, you cannot consider the full length as a anchorage length. No, you have to satisfy the horizontal length and L extension this depth, and also the radius diameter. So three requirements shall be satisfied independently. Again, this equation is for LDH in ACI 318.19. This is equation for LDH in ACI 318.25. This equation will result in a very significant lower value than the equation of ACI 318.19. So take care. As you can see here, this is the commentary of ACI 25. Revisions to 25.4.3.1 introduced in ACI 318.19 were found to result in appreciably increased value of LDH for common cases. This is the same what I have said just right now. Also, if you'd like to develop your bars using headed deformed bars, you have to use a different equation, LDT, LD or L sub DT, Also, if you increase the yield strength, this LD sub DT will be increased also. Also, lab splice links, you have to understand that this requirement along the lab splice, what I showed you before here, along the development length. So if you look for the both provisions, you will feel both of them are identical. But this is for the lab splice. So along the lab splice, not the development link. Development link is something different. Lab splice, in fact, is a function of development link, by the way. The code need you to provide a transverse reinforcement of a certain spacing to satisfy a value of specific K sub TR, as we mentioned just before a couple of slides. So sometimes you have to increase the transverse reinforcement to satisfy this requirement. Also, if you would like to calculate the compression lab splice lengths as per ACI 25.5.5, you have to know that the code need longer compression lab splice for high grade reinforcement. So if you look here we have the difference between the compression lab splice for grade 550 and for grade 420. The required compression lab splice for grade 550 is higher than the values required for 420 by a 30% more. Sorry, by 60% more. By 60% more. You have to know that. Out of this 160%, out of the 60% increasing, the 30% is directly because of the ratio of the yield strengths. So you have to know that also, as you increase the strength of the bars, there are many penalties you have to satisfy. So as you can see here, the code permits you to use high grade reinforcement, but you have to satisfy additional penalties on that. Now we will discuss different structural members, as I said before. I will start with two-way slabs. If you look here, if you would like to find the minimum thickness of two-way slabs, you have first to determine the used yield strength. If you look here, for grade 500 megapascal, the minimum thickness required by the code is higher than the 420 megapascal by around 10%. So okay, you can use higher grade reinforcement, but you have to provide more minimum thickness of the two-way slab. But if you would like to use 690, okay, the code here covers 280, 420, 550. Where is the 690? I believe the main my interpretation for that if you would like to use 690, you cannot find the minimum thickness of the two-way slabs. You have to specify a thickness and calculate the actual deflection, because some engineers, they are using this table to avoid the calculation of long-term deflection. In fact, practically this is not the case. We are not using this table at all, but some engineers in some countries, they are using this table. So you have to know that for 690 megapascal, you cannot use this table and you have to calculate the deflection. If you also would like to use a strength of the steel more than 550 megapascal, the modulus of rupture used to compute the deflection shall be based on the reduced modulus value. This value is around 2/3 of the 100% value. The main value is 0.62 square root of FC prime, but here the code permits you to use high grade reinforcement, but you have to calculate the deflection based on reduced value of modulus of rupture. By the way, practically in all of my projects, I have used this value, even though with a grade reinforcement lesser than this value. In ACI 25, I believe this I think this note for the modulus of rupture has been removed in ACI 25. And again, as I said, deflection must be calculated for grades higher than 550 megapascal. What I mean here, if you have a 690, you cannot use the stable and you must calculate the deflection. Okay, also in 2S labs we have in 2S labs chapter 8 we have the stable. This table I think is known for the engineers. Here when you have a connection and you would like to know how much the percentage of the load will be transferred as a flexure and how much the percentage of the load will be transferred as a shear. So to determine this percentage is important for two-way shear capacity. By the way, if you would like to determine this percentage, as you can see here, you have to find the strain or tensile strain. Tensile strain now is function of yield strain. So if you are using high grade reinforcement, you have to you have to calculate first the yield strain, and then you have to calculate this limit. So here the code connects the limit with the grade of reinforcement that you would like to use. Also, now I would like to start the beams section. Also for the minimum thickness or depth of non-pre-stressed beams, as you can see here, the code provides a minimum values for the thickness, but here we have an important footnote that these values are applicable for normal concrete and yield strength of 420 megapascal. But if you would like to use a high grade reinforcement, please you have to multiply these values by this factor. So as you increase the used yield strength, these values will be higher. So for grade 550 megapascal, the minimum thickness may increase by around 18%. So here I'm trying to help you to connect how you can understand the additional requirements on using the high grade reinforcement. Okay, here also, for minimum flexural reinforcement, the maximum value that can be used to compute the minimum flexural reinforcement of the beams is 550 megapascal. So let's assume that you would like to use 690 megapascal. You have, when you would like to calculate the minimum flexural reinforcement, you have to use a maximum value of 550 megapascal. So if your beams, let's say, are governed by the minimum value, you cannot take the full benefit from 690 megapascal. The maximum value can be used at that time is 550 megapascal. Okay. Also, again, we have here a limitation on the transverse reinforcement spacing along the development length. So the transverse reinforcement in beams must be provided such that K sub TR is more than a certain value for a grade 550 and a grade 690, regardless of the bar spacing. This is very important. As you can see, the same provision was in the development length and also in lab supplies and also in beams section. Here, for example, this slide was presented by ACI University. Here they need to inform you that, okay, we have used a high grade reinforcement with a 50% of the reinforcement, and we satisfied 88% of the nominal moment. Again, let's assume that we have a section or beam section with a grade 420 megapascal bars. and we have this amount of reinforcement. If we calculate the strength, we will get this value. If we use half of this value of reinforcement, but with high grade reinforcement, we can get this nominal strength. So approximately 50% of reinforcement achieved 88% of the nominal moment. But again, we cannot look to this example from one single angle. We have to look for other penalties in the code. Here you saved reinforcement, but what about the additional requirements of transverse reinforcement, about the development length? So you have to look to the full pictures. Also, you have to be care that if you change the grade of reinforcement, tensile strain also will be changed. Typically, our calculations are based on the tensile strain equal to 0.005. In fact, this assumption is correct for a grade 420 megapascal. But if you increase the yield strength of the bars, this value will get higher. And this will change the design of your section. So this is also the same requirement, but in the lap splice of the beams. The code need you to provide a transverse reinforcement with a certain spacing along the lap splice within the beam if you would like to use a high grade reinforcement. Okay, now I would like to start the column section. Here I would like to highlight that in columns and walls, it's permitted to use high grade reinforcement up to 690 megapascal. Again, this depends on your system, structural system. But if you look here, the maximum axial compressive strength shall be calculated based on the maximum value of 550 megapascal. So even though you would like to use 690 megapascal, you have a maximum limit on the calculations of maximum compressive strength. So this also you have to keep in mind. So if we look for this example, for 80 KSI, here we have the same section, the same amount of reinforcement, but in first case, the grade of the bars is 80 KSI. In the second case is 100 KSI. Both of them, the maximum compression is the same. Why? Because as per the code, the maximum axial compressive strength shall be calculated based on 80 megapascal, 80 KSI or 550 megapascal. So yes, here we increase the strength, but the maximum compression is still equal to the same case of 80 KSI because of this limitation. If you look here, for example, we have a curve for a red curve is for grade 100 and a blue curve is for grade 80. As you can see here at this point, both of the grades are intersecting the same point because of this limit. Okay, redistribution of moments for flexural members. In continuous flexural members, ACI code permits you to make a redistribution of moments due to some rotational capacity in the connections. As you can see here, as the grade of reinforcement increase, the permissible redistribution decrease. So at this limit, for example, if you would like to use 550 megapascal reinforcement, the maximum redistribution percentage is 10%. But if you'd like to use 420, we can go up to something in between 10 and 15. So as you increase the grade of reinforcement, the allowance of redistribution decrease. Okay. Now for intermediate moment resisting frames. In intermediate moment resisting frames, we can use only grade 60 or 420 or grade 80, 550 megapascal. Now, if you look here, the spacing of the transverse reinforcement depends on the grade of bars. So if you would like to use higher grade of bars, the code need you to provide smaller spacing to prevent the buckling. So this is also another type of penalties from the code. Also, this beam section also for let's say special moment frame. Here, the minimum size of the column, again, this is for special moment frames. The minimum size of the column depends also on the grade of the bars. If you would like to use a higher grade, let's say grade 80, you have to provide more width for the column. And also, the reinforcement here required along the body of the beam also depends on the grade of the bars. If you provide higher a grade of bars, you have to provide a different amount of reinforcement. Here also, spacing at the plastic hinge region. Spacing also depends on the grade of the bars. If you would like to use higher grade reinforcement, the spacing will be lesser. Also, if you have a beams with a factored axial force more than this limit, as per the code, the maximum hoop spacing at least is the least of the following: 6-inch or 6 diameter the main bar of the smallest grade 600 enclosed longitudinal beam bar, or 5 multiplied by the diameter of the bar if you would like to use a grade 100 a grade 80. Again here, if you would like to use higher grade, you have to use a smaller spacing. Also, for the columns, the dimension limits for the beam column joints also depends on the grade of the reinforcement. If you would like to use higher grade reinforcement, you have to provide more width. Here also the same issue, spacing of the transverse reinforcement depends on the grade of the rebars. Also, for joints in special moment frames, concrete used in joints with a grade 550 longitudinal reinforcement shall be normal weight concrete. You cannot use lightweight concrete. This also another penalties on using high grade reinforcement. Also, for special structural shear walls, you have to know that the maximum vertical spacing of transverse reinforcement also depends on the grade of the primary flexural bars. If you look here, if you would like to use 690 megapascal, you have to provide a transverse reinforcement with lesser spacing. For 420, the spacing, for example, is 6 diameter, here 5 diameter, here 4 diameter. Okay, also for the diaphragms in seismic design, by the way, you have to know that in ASI code we have a chapter to design the diaphragm, chapter 12, I think. That's for seismic design category A, B, or C. If you would like to know the additional requirements in case of special systems or diaphragms in building assigned to seismic design category D, E, or F, you have to check chapter 18, section 12. By the way, here, if in the diaphragms or diaphragms in buildings assigned to seismic design category D, E, or F, it's not permitted to use the mechanical supplies for grade 80 and grade 100 KSI. I think this provision now changed in ACI 25, or has been changed in ACI 25, and now ACI 25 permits to use the mechanical splices at this area, but with a certain type or certain class, say like class S. By the way, now mechanical splices types are totally different in ACI 25. Okay, table 20.2.2.4a permits the maximum design yield strength to be 550 megapascal for portions of a collector, for example, at the near critical sections. Also here, another penalty on you if you would like to use a strength higher than 550. So the upper limit here is 550. Again, this is for special systems. Also here, we have a limits on concrete compressive strength. As you can see, for a special moment frames with a grade reinforcement 420 or 550, the minimum FC prime shall be 21 megapascal. But if you would like to use a 619 in special shear walls, the minimum FC prime is 35 megapascal. So here also other requirements on the compressive strength related to the grade of reinforcement. Strength reduction factor. I'm not sure if it's recording or no. Okay. Strength reduction factor. As you know, in ASI code, if you would like to compute the design strength of any section, you have to know first that this section is tension controlled, compression controlled, or in the transition region. If tension controlled section, the strength reduction factor is 0.9. But if compression control, the strength reduction factor can be 0.65. Anyway, in ACI 2014, if you look here, the tensile strain was compared to the 0.005. I will zoom here. 0.005 and the yield tensile strain. In fact, this is in ACI 2014, but in 2019, the formula changed a little bit. Now, the code, instead of 0.005, the code needs you to calculate the actual strain based on the yield strength. So, if you would like to use a high grade reinforcement, this value will change. If you look here, this maybe can be more clear. If you look here, this picture presents the variation of strength reduction factor with a net tensile strain. This is ACI 2014. Here we have a fixed value. In fact, this fixed value was based on yield strength equal to 420 megapascal. Now in ACI 2019, as we can use high grade reinforcement, this value shall be calculated based on the actual or based on the grade of reinforcement that you would like to use. So this value will not be the same if you would like to use a grade 550 or 690. So 400, if you would like to use a grade 420, this value will be 0.005. But for grade 550, this value will be 0.00575. For 6090, this value will be also higher. This again will affect the sectional design of your member. Okay, here also I need to highlight that this curve, black curve, is the interaction diagram for this section as per the rules of ACI 14. But here we have a little bit change in the shape of the interaction diagram if we would like to use 318.19. So if we have a point here or load combination here, this point is safe in ACI 2014 but not safe in ACI 2019. So this area or the main reason for the not matching between the two curves because of the additional requirements on high grade reinforcement. In fact, again, the benefits of high grade reinforcement can be sometimes to reduce the congestion, let's say congestion between for the reinforcement, improve the concrete placement, in fact lower the placement cost as you reduce the number of the bars, smaller member size, more usable space. By the way, The benefits, again, not guaranteed totally. Sometimes if you provide more reinforcement with more strength, this will not improve the strength of your section. This depends in fact on the location, this depends mainly on the shape of the interaction diagram. Where is your governor load combination? It's here or here or here or here. So in some locations the reinforcement contribution will be very low. Here also, the main idea that if you'd like to take the maximum benefit from using high grade reinforcement, try to use the maximum grade reinforcement with maximum concrete strength. As you can see here, as we increase the strength of the concrete and also we increase the yield strength of the bars, we will get the least size of the section. By the way, again, this is based on axial force only. If we have a moment, the equation will change. We have discussed a lot of requirements in different seismic design categories. So before using the high grade reinforcement, you have to check the additional requirements in seismic design category A, B, or C, or special requirements for special systems. For ACI 350-20, this is for the environmental structure. In fact, this code mainly is integrated with ACI 318-11. It's not integrated yet with ACI 318-19. That's why if you open this code, you will find that the main equations, formulas, and trains are based on grade 420. The maximum yield strength permitted for the environmental structures is 550 megapascal as per the code. As you can see here, 550 megapascal. But the shrinkage and temperature area reinforcement used in the environmental structure as per the ACI 350 must be based on a grade 420 megapascal. This is very important. Here I need you to read the manual of ETABS carefully. ETABS can take some additional some requirements for using high grade reinforcement, and a lot of requirements you have to satisfy by yourself. For example, the limits on the FC prime you have to satisfy by yourself. ETABS maybe can take the some requirements I will show you. For example, the upper limit on the maximum compressive strength is taken by ETABS. The strain also is calculated by ETABS based on the grade of reinforcement. This is a good point. Here also the area of reinforcement for special members also is based on the grade of reinforcement, as we have discussed before. Also, as you can see here, for special moment resisting frames, the area of reinforcement is based also of the grade of reinforcement. Here I got an email from CSI staff, so CSI technical support, that I was in fact assuming that the ETABS always consider the tensile strain for tension controlled section is 0.005, but they inform me no, that the tensile strain is calculated using this equation. This is very nice. I believe that I have finished this. In fact, finally, I would like, for some people they don't know, that I have published a new course. The name of this course is The Design Journey, 9 hours. I have discussed, in fact, the real design project from the first step to the last step. In fact, I spend a lot of time to try to make the content easy for people. In fact, I didn't waste the time on the in the detailed calculations that can be found anywhere, rather than concentration or concentrating on the main concepts that you need to complete your real design from A to Z. Thank you, engineers. I hope this topic was useful for you, and have a nice day.